In this video, we're going to add a strong acid to a buffer solution of a weak acid and its conjugate base. So we're going to use acetic acid. So HAC, so vinegar, is in equilibrium with H plus and AC minus. So we have our acid because it can give up H plus, its conjugate base because it can consume H plus. And we're going to put both of these in the solution. It's easy enough to find vinegar, and you could obtain sodium acetate as a solid, dissolve it, and so you can add both the acid and the base of your weak acid-base conjugate pair into solution at the same time. Just for our cases, let's say we'll do this all in 1 liter so that our molarity equals our moles, and we're going to have 0.010 mole of our acetic acid and 0.0050 mole of our acetate, the anion. And to this solution, we're going to add strong acid. Well, before we add the strong acid, I just have a buffer solution. My Ka is 1.8 times 10 to the minus 5. Go ahead and solve the pH for this one. Pause here, solve the pH for the buffer before we've done anything for it. Well, if you're back, so remember that our Ka equals the H plus, the AC minus over the HAC. So it's your H plus and your base divided by your acid. This is always the setup for our buffer. This is always the setup for our weak acid-base solutions. And so I just need to plug in our values here, solve for that H plus. I've got Ka as 1.8 times 10 to the minus 5. Our acid, well, it's that many moles in 1 liter, we said, so it is 0.010 molar. Our base, same idea, 0.0050 molar. Rearrange, solve for our H plus. We will get 3.6 times 10 to the minus 5. Take the negative log of that to find the pH. And the pH of our starting solution here comes out at 4.44. And so our initial solution has a pH of 4.44. And then we're going to add strong acid. We're going to add 0.001 mole of HCl to this solution. Normally, if you just have strong acid, like HCl, it will break apart and just make that much H plus and Cl minus. As a result, if you put in 1 liter 0.001 mole of HCl, you'll end up with 0.001 mole of your H plus and 0.001 mole of your Cl minus. It fully separates, which means you have a H plus concentration of 0.001 mole of H plus in 1 liter, or 0.001 molar. Plug that in, find your pH. Your pH equals 3. Remember that neutral water is pH 7. So by adding 0.001 moles of HCl to a liter of water, we change the pH by 4 numbers, from 7 to 3. What we're going to see when we add it to the buffer is that we're going to have a much smaller change, because our buffer, HAC, in equilibrium with H plus and AC minus, well, initially we have 0.010 moles of our HAC, and we had 0.0050 mole of our AC minus. But when you add H plus from a strong acid, it has to be kicked free. What really happens is if you have an HAC and it runs into that H plus that was created from the strong acid, they just bounce off. HAC already has its H plus. It doesn't need another. But if there's an AC minus around, and there's suddenly a lot of H plus from a strong acid, they will absolutely react to make HAC. Strong acid will consume the weak base. The strong acid has to get rid of its H plus, and it's going to slap it onto the weak base. There's something there to put it on that's better at picking it up than water, and so it will absolutely attach it to our anion. Well, when H plus and AC minus run into each other, you create the weak acid. So not only does it destroy some of the weak base, it simultaneously creates weak acid. This is what happens when you add a strong acid to a mixture of a weak acid and base. It changes the amounts. Because what we're going to find, well, if I add 0.001 moles, so plus 0.001 mole of HCl, it's going to find and destroy that much AC minus. So we're going to lose some of our AC minus. And each time it does that, it creates some of our weak acid. So it's going to create 0.001 mole of our weak acid. This means they'll react and we'll have a new concentration. 0.011 mole of our HAC and 0.004 mole of our weak base. If you were just given these two concentrations and told to find pH, you'd have to do the calculation to find it for this mixture. It's different than our original mixture. And this is exactly what happens. Adding the strong acid changed how much our mixture was composed of. We have a little more of our weak acid, and we have a little less of our weak base. This is going to shift the equilibrium, so we have to recalculate. We have to find pH again. Well, our Ka is still going to equal whatever the balance will be from this equilibrium for H+. Our new AC minus of 0.004 instead of 0.005. And our new HAC of 0.011. So we've shifted it just a little bit. Our Ka is still the same, 1.8 times 10 to the minus 5. So rearrange, solve for our H+. We find 4.95 times 10 to the minus 5. If we want to find the pH of that, we get 4.305. And so our pH is different. It's a little smaller. Previously, our pH had been 4.44. We added strong acid and we go down, more acidic. But the change here is only by 0.135. We'd said that strong acid, when added to pure water, changed it by 4 pH units. But the same amount of strong acid added to our buffer changed it by 0.1 pH units. The difference in behavior is that a strong acid in pure water, those H pluses have nowhere to go. So if you have some HCl's and you put them into a container full of water, all that can happen is the H plus just still exists. It floats around, and our pH is simply the amount of H plus, negative log of that concentration. But if there is AC minus around, those H pluses can pair up, and then they're not in solution. They're not freely floating, hanging out on their own anymore. And so by having something it can react with, it changes the amount of H plus that is released due to the strong acid. The less H plus that ends up being released, the less the change in the pH. This is the advantage of a buffer, and this is how they respond to a strong acid being present. They will consume the weak base and create weak acid. changing those concentrations and thus changing the calculation of the equilibrium.